and welcome back to Calculus 1 on this glorious Saturday morning, right? Section 3.5, trigonometric derivatives or derivatives of trigonometric functions, or just for lazy people, trig derivatives. That's it, done. We are going to take a look at 6 trigonometric functions and their derivatives. We will see how they're paired, put in groups. And we'll see some similarities, differences between the actual answers, right, the derivatives. And that will be it for the section. It's a fairly short section. What makes this section long is the proof for one of these, where in order for us to understand the proof, we have to memorize 2 limits, which you are actually going to discover how to do all the way in chapter 4. So we are memorizing 2 limits so that we can do the proof, and then in 4.8 we realize how those limits are obtained. Which is kind of interesting, because in order for us to understand in 4.8 how to get those limits, we have to use derivatives, and derivatives are defined through limits, so this is like that loop that makes no sense. But it works. So what are we memorizing? We are memorizing for now, and we'll discover later, is that limit x goes to 0 of sine x over x is equal to 1. That's what we are memorizing. And we are memorizing 1 for the cosine, where the limit of cosine x minus 1 over x as x goes to 0 is 0. So these 2 limits are now just served. So just, there you go, eat this. And then we are going to figure this out in 4.8. Now, why are these limits important? These limits are important to help us with the proof of the sine x. So limit h goes to 0 of sine of x plus h minus sine x over h, and then we just unleash the procedure. 3 steps. Sine x cosine h plus sine h cosine x minus sine x over h. We take the first and the last, we put them together and factor out sine x. So limit h goes to 0, take the first 2, factor out sine x, we get cosine h minus 1, everything is divided by h, and then we have minus sine h cosine x over h. And if you take a look at this, right, this part over here is 0 because of the definition of the limit up there. That part is 0. So from the first part we just have sine x minus, and then over here we have the limit of h goes to 0 of what? Oh, wait, hold on. That's 0 times sine x. That's what I meant to write. Sorry, 0 times sine x. And then over here you have limit of sine h over h times cosine x. Now this part goes to 1, and the whole thing is cosine x. Right, 0 minus the hell. Oh, it's a plus. It's this sign. There we go. So it's cosine x. Awesome. So what we just proved is that the derivative of sine x is cosine x. Much nicer definition of this in Calc 2 at the end in chapter 9. But then this is the first time, this is the standard way to prove any derivative, we unleash the limit formula for it. And then this should be a standard proof on, so either this one or the cosine one on honors exams. So that's what we have. So you have a trade-off. You either unleash this procedure every time when you need to find the derivative of sine x, or you just memorize that derivative of sine is cosine. You pick between the two. Now, what are the other 5? The other 5 would be that derivative of cosine x is negative sine x. Derivative of tangent x is secant squared x. Derivative of cotangent x is negative cosecant squared x. Derivative of secant x is secant x tangent x. And the derivative of cosecant x is negative cosecant x cotangent x. Yeah, I can't fit all 6 of them the way I wrote it, but you can see at least, you can see most of them. All right, so we are watching, right? Well, we're looking at all these 6 derivatives, and don't worry about it. First, observe the pairing. Anytime you see a sine, it's a cosine. Anytime you see tangent, there is a secant, and cotangent and cosecant. These pairs are never broken. Look at that. Do we all see what we call trig pairing for calculus? Calculus trig pairs. Now, the fun part is that these functions are paired the same way to Pythagorean identities. Remember how tangent squared plus 1 is secant squared, right? So the same pairing is preserved. So we have sines with cosines, cosecants with cotangent, and secant with tangent. That's the first part. Now look at the derivatives of all the cos. The c. Derivative of cosine, negative. Derivative of cotangent, negative. Derivative of cosecant, negative. Do you see that? It's also called symmetry in these equations. Do we also see how tangent and cotangent both have the other one squared? Guys, these formulas are highly symmetric. Technically, learning the first and the third and the fifth will immediately give you second, fourth, and sixth, if you know the pairing. Remember the minus signs, right? So whatever way you choose to learn this, but know it very well, because a lot of stuff later on, especially in Calc 2, depends on this. Switching the screen, Chapter 7, Calculus 2, sections on Calculus 2, and look what it says over here. Trigonometric integrals, trigonometric substitution. When you look at these sections, obviously everything will be trig. So to be able to do any of these, you will have to use something called U substitution, which involves derivatives as well. Integration will be backwards. You will say that the integral of cosine is positive sine. Same formulas, you just read them backwards. So you are learning now for the next 3 classes. Calc 2, Calc 3, differential equations. Okay? You are learning these 6 formulas, and they will be repeated whether you read them forward as derivative or backwards as the integral. They will be repeated and recycled over and over again for the next 3 classes, so including this one, 4 classes. Your 4 grades depend on you learning this now. So don't confuse these things. Make sure you have these formulas straight in terms of what goes where. And that will be it. The section is over, right? Except, let's see. Do we all know product rule? Do we all know quotient rule? Nice. How about exam question? Prove derivative of cosecant x. I'll even leave the cosecant answer so you can see it. This should be a standard honors question, but it's cool to be a replacement question on the regular exam. Fine. So how do you solve this? What do you do? Break it down into what? 1 over sine. And then do what? Big formula called quotient rule. Good. So, rewrite it as 1 over sine and unleash quotient rule upon it. Those of you who forgot the quotient rule, right? 3 steps. 3 steps, trig identities. You should be able to pull this off for tangent, write it as sine over cosine, and technically anything else. It goes really quick. Remember how you can do the product rule as well? Let's see. How does the product rule work? Times, I don't know. Let's see the product rule. You all got cosine? Right? I know. I know. Trig is beautiful, all right? It's beautiful. It's the most amazing stuff in the galaxy, okay? Periodic functions, you know, describe waves. All right. I really don't think there's anything else I can say. We're going to cover in the chain rule something that will fix if they put those formulas here. I don't think they did. All right, so the last question. Which could be also a cool exam question. So what's the 307th derivative of sine x? Negative cosine x? Yeah. Yep. Nice. Negative cosine x. That's the reason why he has such a good grade. He's able to take 307 derivatives like this. I know. Amazing.
Divided by 4.
Yeah.
And when you get
So, yeah, when you get
you get 0.75, it's negative. You get 0.25, it's positive. And then if you get 0.5, it's
ah, Okay, well, it's difficult to follow that way when you say it that way, but you did exactly what you got the right idea. All right, so this is what we're going to do. A function is sine x, right? That's the kind of zeroth derivative. And then the first derivative is cosine x, right? So if you start strong by actually taking these derivatives, because you know you can take second and third and so on. So f of x, which is the zeroth derivative, is sine x. And then the first derivative, cosine x. Second derivative is negative sine x. Third derivative is negative cosine x. And then the fourth derivative is what? Sine x. Recycle. So this is going to be the fourth, fifth, sixth, seventh. Recycle. 8, 9, 10, 11. Go back. 12, 13, 14, 15. Go back. 16, 17. And you just keep writing until you reach 307. Or you do what you did, which is divide by 4. And look at the remainder, right? You divide this by 4. You see that you are one shy of actually being divisible by 4. So you're technically dividing only 7, because 300 is evenly divisible. So this is your 304th derivative. Anytime you have an evenly divisible by 4, you go back to original sign. So 304, 5, 6, 7. 307, right there. So you can see that every time when the order of the derivative, 0th derivative, 4th, 8th, 12th, 16th derivative, they all go back to the original sine x. So all you need to do is to take a look at the last two digits, and if they are evenly divisible by 4, right? Now, what was he saying about 0.75, 0.25? Well, when you divide the number, your remainder is either 0.25, which is a quarter, 0.5, which is half, 0.75, which is 3/4. So here's your remainder 0, remainder 25, remainder 50, and remainder 0.75. And then cycles back. You're not supposed to memorize these things. What you are supposed to do is reason with it, because on the exam, this changes if I say what is the 317th derivative of cosine x, right? Then you have to write the cycle for cosine, which is shifted. And that's it. We say bye to the stream. Do we have viewers? Yeah, we have one. Hello, viewer. And that's it. Well,